So now in inorganic chemistry, you're going to study three things. One of them is the starting of the first one, that's period 3. Then you're going to do group 2. And then you'll have group 17. And finally, at the end, there is going to be nitrogen and there's going to be sulfur. Okay, so but it's all a lot about data that you have to memorize. So starting with the first one, okay, this is here's your so here's your first thing about period 3. Period 3 has these elements. It's got sodium, magnesium, aluminum, silicon, phosphorus. So I'll just go through the notes, and that's pretty much. We'll be done with inorganic. Okay, so inorganic, all 4 chapters will be done with very quickly. So you've got sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And this is how the melting points actually look like. The melting points of sodium is kind of low. It's 98 degrees centigrade. Okay, so sodium melts very quickly. Phosphorus is 44 centigrade. You don't really need to exactly remember what the melting points are. You just need to know which ones are high and which ones are low. Magnesium, aluminum, and silicon have very high melting points, and phosphorus, sulfur, chlorine, argon, they've got very low melting points. So the first question is, we'll talk about in detail about the first 3, sodium, magnesium, aluminum. They're all metals. They've got metallic bonds. So they're supposed to have high melting points. So what is a metallic bond really? It's a bunch of positive metal ions in a sea of free moving electrons. That's what a giant metallic lattice is. Okay, you've got and I'll add this. So I'll add this. What a metallic bond is, that it's a regular arrangement of metal ions. Okay, just like your O-level stuff. So regular arrangement of metal ions in a sea of free moving electrons. So in a sea of free moving electrons, that's what a metallic lattice is. Okay, Unad, is this clear?
Yes.
Okay. What happens is the electrons and the positive ions, they're kind of attracted to each other. So there's the free moving electrons in the middle, and these electrons are going to be kind of attracted to the positive metal ions surrounding it. The positive ions will be kind of attracted to the, I mean, like if you try to remove this positive ions, it's going to be, you won't be able to remove it because the surrounding electrons will attract it. So basically the force of attraction that you have, it's this thing that so the force of attraction that you have in a metallic bond, okay, that's a force of attraction that exists between positive metal ions and the delocalized electrons that you have. Okay, so that is what the force of attraction is. And there's going to be an electrostatic force that is going to exist between them. So there's going to be an electrostatic force of attraction. Now, since there's going to be an electrostatic force of attraction, so what happens is, why does magnesium have a higher melting point? Because the metallic bond is twice as strong. The reason is that when you go from sodium to magnesium to aluminum, 2 things are happening. You've got more delocalized electrons. Like sodium will only have 1 delocalized electrons, but aluminum, on the other hand, will have 3 delocalized electrons. And the other thing is that the charge in the aluminum ion is going to be a lot bigger as well. So if you look at aluminum over here, in aluminum, the charge on the ion is going to be a lot higher because it's going to be +3. It's not going to be just any positive ion, it's going to be a +3 ion. And the number of delocalized electrons will be a lot greater as well. So you got stronger metallic bonds. The positive ions have a higher charge density, and you got more delocalized electrons, so there's going to be stronger attraction. So sodium is going to have a lower melting point. Magnesium is going to have an even higher melting point. Aluminium, on the other hand, will have an even greater melting point. Is this clear? This thing, you clear about?
Yes, yes.
And the melting points are for magnesium. The melting point is, you don't have to remember this part. It's so all of a sudden, sodium was actually 98 degrees centigrade, was very low. Magnesium is what, 650 degrees centigrade. Okay, so that's 650 degrees centigrade. And then you've got aluminium, and aluminium is going to have an even higher melting point. That's 660 degrees centigrade. Then you might also get a question about this, and that is why is the melting point from sodium to magnesium? Why is there such a big difference? Why is there a much smaller difference between magnesium and aluminium? And the reason is that when you go from sodium to magnesium, the strength doubles because the number of delocalized electrons, they double, and the charge on the ion also doubles. You had a +1 charge in sodium, and you've got a +2 charge in magnesium. But when you go from magnesium to aluminium, what happens in that case is that the charge does not double, actually. It just increases slightly. You go from +2 to +3. So that's not a doubling of charge. And the number of delocalized electrons. So every atom losing 2 electrons, now every atom is losing 3 electrons. So over here, the number of electrons and the charge doubles, but over here it does not actually double. It just increases 50%. So which is why the strength does not increase that strongly. Over here, it increases very, very strongly. Is this idea clear as well?
Yes, sir.
So then the next one is you've got so that's about sodium, magnesium, and aluminum. You'll be asked about explaining the melting points. Then you've got a very high one, which is silicon. Silicon's got a very high melting point. So what's the reason for that? The reason for that one is that silicon has a giant covalent structure. It's so this is for silicon. It's a giant covalent structure, and it's got a large network of very strong covalent bonds, and they need to be broken. So a lot of energy is needed to do just that. Silicon's melting point is going to be extremely, extremely high. It's a structure that's very similar to actually diamond. So the melting point is around 1410 degrees centigrade. So that is silicon's melting point. So you got a large network of very strong covalent bonds in the giant covalent structure. Is this clear?
Yes, sir.
So here you've got this part, which is phosphorus, sulfur, chlorine, and argon. So what happens over here is that when you have phosphorus, sulfur, chlorine, and argon, what happens over here in this case is, okay, these are simple molecules. They all have very low melting points. And why do they have such low melting points? The answer is that when you have simple molecules, they don't have anything to do with each other. All these simple molecules, these are the structures of all these simple molecules. Chlorine is usually just Cl2. Phosphorus is P4. That's the formula of phosphorus. Cl is diatomic, it's Cl2. Phosphorus is actually P4. Sulfur is usually it's S8. And argon is just Ar. Here, that is what argon is. Those are the formulas of chlorine, phosphorus, sulfur, and and argon. And those are not the only formulas. There's a lot of other forms of phosphoruses that exist. So phosphorus allotropes, like you've studied allotropes of carbon. Phosphorus also has a lot of allotropes, uh, which are basically different structures. You've got, you've got all sorts of different examples. Like these are over here. Remember, the arrangement of atoms in a molecule there could be many different arrangements. So you can see over here that it's like if I open the image in new tab, so you'll notice that there is a thing called diphosphorus where phosphorus is actually forming a triple bond. Okay, there's a thing called white phosphorus, which is this one. That's B4. That's the one that we talked about. There's blue phosphorus, there's black phosphorus, there's other arrangement, there's red phosphorus. The more common ones, when you talk about phosphorus, it's usually the white phosphorus and the red phosphorus. The red phosphorus has a, and all of them will have different melting and boiling points. So just like carbon in diamond and graphite, the arrangement of atoms in a particular substance, there could be many different arrangements. So same thing happens with phosphorus as well. P4 is the more common one. Okay, so when you usually talk about phosphorus, the more common one is actually the white phosphorus that you have over here. This is carbon and you've got diamond and you've got graphite, right? So same thing happens in this case as well. I said, but coming back to this, I just did one example. But remember, there's going to be a diversity in the way the atoms are going to be arranged in a particular element. Is that clear?
Yes.
So there's going to be a lot of diversity. And so the next thing is, okay, well, how do you, and the same goes for sulfur. The exact same thing goes for sulfur as well. Sulfur's got a lot of allotropes as well. And there are many ways of arranging the sulfur atom as well. But again, so you've got all these formulas of sulfur. So there's an S2 as well. There's S with 3 sulfurs connected. There's an S with sulfur with 4 sulfurs. There's a 5 sulfur one. The more common one is the S8 one. That's the more common one. That's the one that's the yellow sulfur that you have. That's this one. But keeping allotropes aside, we'll just take one example at the moment. And we'll talk about intermolecular forces slightly. You've got a simple molecule and you've got another simple molecule. These molecules have no attractive force. They don't really attract each other because they don't have a charge. The other one doesn't have a charge. So the attraction is going to be extremely, extremely weak. It's known as van der Waals forces. So I'll explain how would two Cl2 molecules attract each other. What is a van der Waals force? What happens in a Cl2 molecule is, okay, you've got electrons in the middle and you've got electrons over here. What happens is, okay, the electrons are evenly distributed. And since they are evenly distributed, the electrons remain exactly in the middle. Yeah, is this point clear? That it doesn't have an overall charge. Is this clear?
Yes.
But what happens is that the electrons are constantly not in one position. They're fluctuating. So due to some random collisions, the electrons might get knocked to one side. If they get knocked to one side, that side will have a slight negative charge and the other side will have a slight positive charge. Okay, so the electrons might get pushed to one side. And when it gets pushed to one side, there's going to be some polarity that will develop because the electrons, for some random reason, have been pushed to one side. That's known as a temporary dipole. Dipole means two poles. So the molecule now has two poles. But that only happened temporarily. Maybe in the next second, the electrons get evenly distributed again. So it doesn't have a temporary dipole anymore. And maybe in the next second, the molecule collides with another molecule and the electrons get knocked to the left side. So that side will become negative and that side will become positive. Right? Is this idea clear? That's known as a temporary dipole. Is this clear?
Yes.
And the same thing will happen on the other one as well, but that's going to be induced because if this side is positive, and imagine this molecule flying around and it comes close to this, its electrons are going to be attracted to the positive side of this other molecule. This side is positive, so its electrons are going to get attracted to it. So this side will become negative and this side will become positive. That's known as an induced dipole. Okay, that thing is known as an induced dipole. Now, at this point, the molecule has a positive side and it's got a negative side, and they're going to attract each other. The negative side will attract the positive side. So there's going to be an intermolecular force, and that intermolecular force specifically is known as van der Waals forces. So van der Waals forces exist because there's fluctuation that's happening in the molecule. This entire thing is called a van der Waals force, or it's known as a dispersion force. Okay, that's what this intermolecular force is. Did you get this part?
So intermolecular is the same thing, right?
Yeah, it's the same thing. In intermolecular force, you've got other types of forces as well. So van der Waals forces is one of them, right?
Okay.
And there's going to be fluctuation that's happening. The electrons in the molecule in the next second, there will be no dipole. Maybe in the next second, the electrons get knocked to this side. This side will become negatively charged, and this side will become, it's going to have a temporary dipole. The negative side is going to push the electrons in the other molecule, which is next to it, and that side will become negatively charged. This side will become slightly positively charged, and they're going to attract. So they're going to attract each other. So there's going to be some force of attraction that will always exist between these molecules. Is this idea clear?
Yes.
अच्छा अब ये कि so you've got these van der Waals forces. So the molecules, all these molecules are non-polar, and they're tiny molecules, and they'll have these van der Waals forces, which have intermolecular forces. Now the thing about these intermolecular forces is, the bigger the molecule, the bigger the dipoles you're going to have. Like phosphorus over here has a total of how many electrons? It's got 15 electrons each, so that's a total of 60 electrons in a phosphorus molecule, right? I mean, this entire molecule has 60 electrons. So imagine if the 60 electrons, for some odd reason, they get knocked to one side, very, very slightly. Maybe they get knocked to this side. So the dipole that's going to be created is going to be extremely big in size. Is that idea clear?
Yes.
Like in the chlorine molecule, you had fewer electrons, 17 electrons in chlorine, 17 in the other one. So that's a total of 34 electrons, right? So if 34 electrons get knocked to one side, there's going to be a negative charge on one side, and there's going to be a slight, and the electrons are getting knocked to one side very, very slightly. But the dipole that's going to be created is going to be slightly weak. But over here, if it's 60 electrons, the dipole is going to be very strong. And the same thing is happening in the other one. So the attraction is going to be a lot stronger. In sulfur, what happens is that you've got 16, 16, that's 8 times 16, that's I think 96 electrons, 16 eighths. No, that's 120, what? 120, 16 times 8, that's 128 electrons, I think.
128, yes.
So you got 128, so you got 128 electrons, right, in this big molecule in total. So imagine if 128 electrons, they drift to one side very slightly. So that negative charge will be like very, very big. So the point is that one rule about van der Waals forces is that the bigger the molecule, the more van der Waals forces you're going to have. Okay, so bigger molecule, you'll have more van der Waals forces. So the biggest molecule out of all of them, out of Cl2, P4, and S8 and argon, the biggest one is sulfur. So it's going to have the strongest van der Waals forces. Why? Because it's the biggest molecule, having the most electrons. Is this clear?
Yes, sir.
And argon being the smallest molecule, it isn't even a molecule in the first place. So this one is the smallest. It's got the fewest electrons. So it's got the fewest electrons, and it's this one. So the order of the melting points for chlorine and all of them, for chlorine, P4, S8, and argon. So the order depends on the size of the molecule. So if you look over here, the graph exactly matches that. The order is sulfur having the biggest molecule, S8. So it's going to have the most van der Waals forces. Argon being the smallest, it's going to have the lowest melting point. Chlorine being the second smallest. Phosphorus being the third smallest. So is this idea clear that all of them have low melting points? They've got weak van der Waals forces, but the weakest is in argon. Is this clear?
Yes.
अच्छा तो ये सारा है. So that's all about explaining the melting points. Then we've got electricity conduction. So who's going to conduct electricity? The first three will conduct electricity. You've got sodium, magnesium, aluminium, and you've got phosphorus. So sorry, the sodium, magnesium, and aluminium. They are the ones that will conduct electricity very well. Why would they conduct electricity? Because they've got delocalized electrons. That's why they're going to conduct. And the other thing about this is that out of these three, sodium, magnesium, and aluminium, aluminium is going to have the best electricity conduction. Why? Because it's got so many delocalized electrons. So aluminium is frequently used for high voltage transmission. It's going to have it's going to be a very good electrical conductor. So why does it have very good electrical properties? That it's got more delocalized electrons. And number two is that it's got it's very unreactive as well. So which is why it's used for high voltage transmission. So it's used for high voltage. Transmission as well. So remember, aluminium is going to be the best electrical conductor, even compared to sodium and magnesium. Is this clear as well?
So even heat depends on delocalized electrons, right, sir?
Even what? Heat? Yeah, heat does depend on delocalized electrons as well.
Mm.
So they're good electric. So you can add that. Okay, although that's not a requirement in the syllabus, but obviously that's true as well. So very good electrical conductor, heat transmitter as well. Achha, but everything they'll ask about explanations for everything. Now, silicon is a semiconductor. You just need to remember that. That's a semiconductor. What happens is that silicon doesn't really conduct electricity. It's a non-metal, but it's like a metalloid. What happens is that silicon has a very low electronegativity. Like if I compare the electronegativity and if I try and find the, so I did have, I think this one. I said, now who wants to lose electrons? Who's got delocalized electrons? The ones, not this, 1 second. I said, this one, let's look at the table. I said, anyways, what I was interested in was the fact that anyone who has delocalized electrons is the one that's less electronegative. It doesn't really like to attract its electrons, right? Like potassium is going to have delocalized electrons because potassium has a very weak electronegativity, right? Is that clear? That it doesn't really like to attract electrons. Is this clear?
Yes.
So now the thing is, silicon is not any element that's very electronegative that will not have delocalized electrons. Like Cl is very electronegative, so a non-metal will not have delocalized electrons because it will be holding on to its electrons very, very strongly. So the electrons are not available for electricity conduction. There's no delocalized electrons either in bromine or chlorine or fluorine or oxygen, right? So is that clear as well?
Yes.
Now, silicon is kind of in the middle, right? It's 1.8. So that means although it is electronegative, but it's not that electronegative. So what happens with silicon is, depending on conditions, that some of its electrons might get lost when you try to conduct electricity, when you try to pass electricity, when you apply a voltage, like when you apply a positive charge, the silicon might end up losing electrons. Why? Because it's got a very low electronegativity. So it's not strongly, it's higher compared to like sodium, but it's still weaker compared to Cl. If it's half as electronegative, almost half as electronegative as Cl, right? So that's why silicon might lose electrons, and those electrons will start conducting electricity. So that's why it's a semiconductor. Is this idea clear that although silicon is a covalent molecule, but electrons will get knocked out from this? Like if you apply a positive charge, a very high voltage, then the atom might start losing a few electrons, right? So is this idea clear?
So, sir, the lost electrons become delocalized.
Yeah, they become delocalized, and so it won't have a lot of delocalized electrons because silicon has still, relatively speaking, relatively a slightly higher electronegativity, but the electrons are not really in its control. So some of them might get delocalized, right? Is that clear?
Yes, sir. Okay.
So which is why silicon is a semiconductor, and what you do with semiconductors is that you make all these chips, all the electronic circuits are made in silicon. Because when you want to make a transistor, you want a substance in which you can etch a microscopic circuit. For example, a real circuit क्या होता है? You've got a real circuit, you've got wires, then you've got stuff that doesn't conduct electricity, right? Like you've got wires, and the wire is coated with what? It's coated with a rubber, right? So basically a circuit is, it's got parts. It's got parts which conduct electricity, and it's got parts which don't conduct electricity, right? You need both things, right? But is the idea clear that for a circuit you need both things? You need insulators, you need conductors as well. I mean, the circuit is made with a conductor, but it has to be insulated, otherwise the circuit will not work, right? Is that clear?
Yes, yes.
So because silicon is kind of in the middle, it's like you can make it conduct, you can also stop it from conducting. Have you heard about N-doping and P-doping?
No, never, sir.
Just although that's not a requirement, maybe you'll study in physics, but I'll give you an idea what N-doping and P-doping is. Like, how do you make silicon conduct electricity? What you do is, like, if I want concept diagram say yoga. I said this one is good. I said, so what you do is, this one also looks good. 1 second, where's the, I guess that's, so let's just briefly go through this. I said, what you do is, you've got this silicon atom, right? It's making 4 bonds. That's it. What you do is, you start p-doping it. What you do is you add some phosphorus atoms to it, right? So what does phosphorus have? Phosphorus has these extra electrons. It's got lone pairs, right? Phosphorus has 5 electrons in its outer shell. Is this clear that phosphorus has these extra electrons?
Yes, yes.
So when phosphorus is present in a bunch of silicon atoms, phosphorus is going to try and make bonds with it. But phosphorus's outer shell electrons, some of them will still be left. So what you've done is in the structure, you've added these extra electrons. That's known as p-doping. You've added some extra delocalized electrons. Do you get the point?
Oh, okay, okay.
So what you've done is you've made silicon have more delocalized electrons by mixing some other substance with it, right?
Okay.
And similarly, there's another thing called N-doping. Although that's a, so what they've done is they've added an aluminum atom now, right? So the aluminum atom bonds with silicon, but the aluminum's outer shell is not complete. So there's space available for where it can accept electrons. So you've got a material that's electron deficient, and you've got a material that's got extra electrons, right? So that's what p-doping and n-doping is. So what you do is you can set up different potentials in the silicon itself. So that's how you make a circuit. You have parts of the circuit that you want to conduct electricity, right? So they start conducting electricity. You have more electrons. You add more electrons by p-doping that part, and you start creating these holes as well in the structure, where you can make the structure electron deficient so that it can easily accept electrons as well. Because there's room available for 2 electrons. There are 2 electrons missing. Aluminum's outer shell is not complete. So in the silicon structure, you've added these holes in it where electrons can be accepted. So that's how you make these complicated circuits at the fine atomic level, right? So you can add so many transistors and so many different circuit elements in a very, very small microscopic nanoscale chip. So is the idea clear? That's what's happening. That's how circuits are made.
Okay.
So that's a good thing about silicon, that you can actually make it, because it's kind of a semiconductor. It can actually the electrons can get delocalized. So you just need to know this idea that a lot of semiconductors, you can make it conduct more electricity, you can make it conduct less electricity as well. So, which is why all circuits are made with this, because silicon is used as it's a very good material for making silicon chips. I said then the last three or last four, they don't really conduct electricity. Why? Because they're all non-metals. They're very electronegative. They hold on to the electrons very strongly. So they're not going to lose their electrons, and the electrons will not be delocalized, and they would be very poor conductors. Although at extremely high potential, they might lose electrons, but even that will happen like they'll still be very poor at conducting. Remember, nothing is there's hardly any substance that has zero conductivity. They'll just be poor conductors. Like Cl can have delocalized electrons, but for that, like if you have a billion Cl atoms, maybe one of them might have a delocalized electron. Is that clear?
So how about argon, sir?
You can have delocalized electrons in argon as well. It has a very low probability. Like argon has it's going to hold on to its electrons very strongly. Argon is very electronegative as well. But the thing is that it would be very hard for it to lose electrons. So if you've got a billion argon atoms, maybe one or two of them might actually lose electrons.
Oh, okay.
So that's why they're poor conductors. They might still conduct, but very badly, right?
Okay.
So that's all about melting points and boiling points and electrical conductivity, right? And then you have to learn a bunch of reactions. The reactions are pretty simple. The first one, the reactions with water of all the period 3 elements. So we can just go through this very quickly. Sodium reacts with water, and it's a vigorous reaction. Sodium is a soft metal with a low density. Sodium floats and fizzes on the surface. It's a vigorous reaction, and you get NaOH and H2 gas. That's the reaction, right? Mg, the reactivity kind of decreases, so it requires a higher temperature, and it reacts with steam. It doesn't really react with water that much. It reacts with steam, produces magnesium hydroxide, which is not very soluble, so you get a weak alkali. It's a similar reaction, except over there you've got a very soluble sodium hydroxide. That's a strong alkali. Over here you're going to get a very insoluble compound. That's a weak alkali. And then you have aluminium. It has absolutely no reaction. Why? Because it's got a non-porous unreactive Al2O3 coating on top of it. So in the case of aluminium does react with water, but all of a sudden it's got this coating on top of it, which is very protective, which is very unreactive. Things can't pass through this. It's very non-porous. So the aluminium stops reacting immediately. So aluminium does not have a reaction, and silicon also does not have a reaction. Why? Because silicon is this big giant covalent structure, so almost no reaction. All of them, the rest of them, they don't have a reaction. Chlorine you can add in swimming pools and you'll get two acids. One is chloric 1, the other one is hydrochloric, HCl and HOCl. Okay, so that these are reactions with water that you just have to memorize. Is that clear?
Just memorize these, sir.
Yeah, you have to
Will they
memorize.
ask for any kind of explanation or something like that? No need.
Not really. Not for this. I mean, you just have to memorize this. I mean, they won't ask why phosphorus does not react with water. It's just a fact, it doesn't really react with water.
Okay.
Same with sulfur, chlorine. So they won't ask any explanation for this. So I guess that's about it. No explanations needed for this. So Tiki will cover the rest. The other ones are just reactions. You just have to remember that stuff. Okay, and I'll share this board link as well.
Okay.
So okay then. Take care.
Okay. Thank you, sir.
Office.